podcast. This is Mr. White.
And Mr. Sadler.
And today we're doing AP plus 2.2.
Two.
And we're trying to apply this concept of velocity versus acceleration and trying to explain the difference, of course. And we're going to relate it a little bit to force, which, of course, is dealing with Newton's laws. And so let's just jump right in. We're going to do all of the problems for you today, so there will be no homework, but we do want to see notes in the logbook about this. So, because acceleration is the change in velocity during an interval of time divided by the duration of the time interval, it is possible to have large accelerations even though the velocity is never high. Imagine dropping a steel ball on a steel plate. Suppose the ball is traveling at 0.5 meters per second, a fairly slow velocity, when it hits the steel plate. So here's my acceleration equation. I've got some velocity of 0.5 meters per second. Now imagine that the ball bounces off the steel plate, reversing its velocity to a value
Of negative 0.5 meters per second.
Okay, in a very short time interval, say 0.01 seconds. What is its acceleration while in contact with the steel plate? Remember to take into account the fact that the direction of the velocity is opposite at the beginning and end. So this negative sign counts.
Okay.
Okay. So
acceleration is just change in velocity over change in time.
So VF minus VI over time.
Right.
So I just take the delta out, and I make it a subtraction problem on the numerator. And so negative 0.5.
Minus negative 0.5.
Well, minus 0.5. For the initial is positive. Divided by 0.01.
Equals 100 meters per second squared.
So in this case, well, depending on what I call positive and negative, this case it's going to be negative 1 over 0.01, so the acceleration is negative 100 meters per second squared.
Correct.
That's a big acceleration.
Right.
So what did we say is the cause of acceleration?
Change in velocity.
Well, no, that's the result. What's the cause of the acceleration? Is
A force.
A force. So is this a big or a small
that's
force?
a big force.
This is a huge force, even though it could be something as tiny as a steel ball.
Right.
Because it's going to have some mass. You're changing its velocity over a very short time interval. So we're talking about a big force required to do this. Okay. Number 2 wants us to take the cushioned approach. Suppose the collision is cushioned by putting some rubber on the steel plate. When the steel ball strikes the rubber with a velocity of 0.5, it deforms the rubber and bounces back. But this time the ball is in contact with the rubber for 0.2 seconds.
So I'm increasing the time by increasing that.
Right. So we're increasing the time with the cushion. What is the acceleration while the ball is in contact with the rubber? It's the same concept.
So the change in velocity is the same.
Right.
It's just the time that's changed from 0.01 to 0.2.
So negative 1 over 0.2
gives us 5.
That gives us a negative 5 meters per second squared acceleration. This is a much smaller force because it's a much smaller acceleration. So what does this have to do with reality? Which is always a pertinent question in this class.
Right.
If we go to the negative 100 meters per second squared, we'd like to think about this catching the ball, the steel ball, with your bare hand. There's not much cushion there on your skin and the flesh and meat part of your hand. So this would be bare hand. This could break some bones. It's going to hurt.
Right.
Versus this, if you catch it right in a glove. So I'm thinking about a baseball
glove.
Catcher's mitt.
Right. The difference between a baseball glove or just getting thrown a ball where it stings your hand.
So this is a tinier force on you because it's in contact for longer.
Correct.
It's slowing down for a longer period of time. So it's a smaller acceleration, therefore a smaller force on you. So that makes I think that makes good sense.
Yeah.
That says assume the acceleration of the ball is constant while in contact with the rubber. Okay, this is not reality. What is the acceleration of the following times? Just after the ball makes contact with the rubber on its way down, well, that would be -5.
Right.
At the point where the velocity of the ball changes from being downward to being upward, it has 0 velocity at this point. So that would still be
The same.
-5. And just before the ball stops making contact with the rubber on its way up, it would still be
-5.
5, because we talk about constant acceleration.
Right.
So if we compared the graphs, let's see, if we compared the graphs of the steel on steel versus the steel on rubber, we would see a dramatic difference. It's going to be hard to sketch this out, but if we just looked at the VT, for example, it went from being positive to negative in our case. Let's take a look at the data here. It went from being positive to negative, okay. So if this is 0.01, this little hash line I made, that means, I don't even know if I can draw this, it's got an acceleration with this kind of steepness. I still didn't get it in that little tiny space because this is only 0.01 seconds of time.
Right.
As opposed to this, okay, so it's 20 of these, so it's like way out here at 0.2 seconds. Okay, in that case, it's really stretched out. And we can see that this is a much shallower slope, therefore a smaller acceleration, and therefore a tiny force, or a
Right.
tinier force, right?
Correct.
So it becomes really obvious there. If we were to analyze the AT graphs of this, this is the tiny one, okay, versus this, which remember was a -100. I can't even scale this as I need to scale this. It would be off the charts. It would be somewhere way down here.
Correct.
It has to be 20 times bigger than this.
Mm-hmm.
So I think that
Explains.
explains it a little bit. So we've related some graphs to forces and acceleration and speed. So if you got any questions, of course, you've got to ask us. Let me go ahead and write that one down. Ask questions. So, signing off, this is Mr. White.
And Mr. Sadler.